Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It's my great pleasure to welcome my collaborator and friend from Trieste, SISSA, who will tell us about our joint work concerning Unital embeddings of sister algebras that one can see. I really love your logo. This is a very nice logo for your talk. I'm very happy you use it. So, Jan, it's all yours. Take it away.
Okay. First of all, I'd like to thank the organizers for the invitation. So, of course, this is the joint work with our main organizer, BRM Hayak. So, yes, I copy and paste your logo here. So I'm glad you like it. So
happy.
Okay, so I think today's talk, I think it's going to be kind of a less technical than the previous ones. I hope. So I think it's already 5 o'clock at least in the afternoon in Europe. So I hope will not bring you too much burden. So okay, so just let's get started. So here's our plan. So here I will start with some motivation and the main results about the embeddings of Kunz algebras and into its matrix algebras. So and then basically I will just outline the proof, and then explain the tools that are needed in the proof. So I think Piotr often called this art of graphs, right? So we play with the graphs and underlying certain type of morphisms to construct our embeddings. So that's the section 3, 4, and 5. So if we have time, so then I would like to give some the geometric interpretations, but so in the framework of C-star correspondence, I think one of the nice features of graph C-star algebras is that you can approach these objects in many ways. Like one of the ways is using C-star correspondence. I think that's called I think the construction goes to like Kunz and Pinster. So they often call the Kunz-Pinster algebras. And then I would just, at the end, if I have time, I would like to just explain some geometric interpretations of some technical conditions about these morphisms. So that's basically the plan. So, okay. So here, let's start with the motivations. So here, the Kunz algebras is basically is the most studied the object in this graph C-star algebras. It's just generated by orthogonal isometries satisfies the sum is equal to 1. So in this Kunz-Kringer framework, so this condition is just the second Kunz-Kringer relation. So here, so the question will be like, to find the unital star homomorphisms among this ON or OQ, right? So it's so from K theory, so
Jan, do you mind if I make a historical remark? Because I find it very interesting. Apologies to the experts who know it by heart. But you see, this algebra was discovered decades earlier by Levitt, and he was trying to solve the following problem: find some minimal ring which would have a property that when you take its nth power and view it as a free module, then it's isomorphic as a module to the ring itself. So Rn is isomorphic to R1, and he was looking, okay, what would be a universal, like minimal construction for which everything else would have to factorize to obtain it. And he derived precisely such an algebra. But then Joachim rediscovered it in the context of sister algebras, and then, of course, he proved that there is an extremely interesting sister algebra that stands behind. I mean, these sister algebras are mind-blowing. I mean, O2 is absolutely crazy. The way it behaves, and it's K0 is 0, for instance. These are extremely interesting sister algebras, and they are part of Elliott's classification.
Yes, I think O2 was started before Kunz. I think it's by Dick Smear.
Yeah. Oh, maybe. Okay. Okay. Yeah. You might be right.
Yeah. Okay. So here, by looking at the K theory, so this the K0 group is the cyclic group of order n-1 for On. So of course, if such a star homomorphism exists, so we have a map on a level of K theory, right? So from one cyclic group to another. So then it's not hard to, so which we are looking at this, then we have this congruence relation, the n-1 must be a multiple of q-1. So for some s in here. So given this so is this condition like sufficient, right? So when given this congruence relation, so then we can indeed construct explicit star homomorphisms from On to OQ. So this, I think it was first written, the formula was first written down in Kawamura's paper in.
Yeah, I mean, this is what we found. I mean, he wrote it down without citing anybody, so we assumed we discovered.
Yes.
But it's important to emphasize, this is why I was playing around with this word explicit, is that we know by a general theorem for this type, this class of sister algebras, that if K theory allows a star homomorphism, then it exists. But it's an existence theorem, not a construction theorem. And here Kawamura gave us very, very explicit formulas, and he didn't cite anybody. But it's kind of amazing when you look at the date. I mean, come on, Conce's algebras are from what, 80s? I don't remember, right? 80s. This is ancient stuff, but this is like 25 years later. So I kind of find it hard to believe that for 25 years, because already in the original paper of Kunz, I think in CMP, in Communication Mathematical Physics, he wrote that if you forget unitality, okay, if you just look at unitals, at star homomorphisms that are not unital, then any Kunz algebra is embedded in another Kunz algebra. Everything goes into everything when you forfeit unitality. But when you demand unitality, after all, these are unital sister algebras, so it's natural to demand unitality. Then you have to obey the rule given to you by the K theory, and you cannot go otherwise. And then you have these very nice congruence relations, but I somehow find it extremely difficult to believe that nobody noticed these explicit formulas for 25 years. For me, it's just unbelievable.
Yeah. So may I come?
Sure.
So it's funny because this is a very natural condition. Because, for instance, n-1 times n-1 matrices behave in the same way. So.
Okay, there is an issue with the sound again. Probably. Wait. So.
Yes, I can confirm, Piotr. So the.
Can you switch it on and off, please? So we'll switch it on and off. But this time I did it. I did my due diligence. I did my due diligence. So I did switch it on and off before the talk. So.
So the volume is fine, but occasionally there is some noise which disturbs.
Hello?
Hello?
Can you hear us now, okay?
Yes.
Now it is okay, but maybe the problem appears when you are speaking for a longer period of time, so we will see probably.
And that's all I can do. We can only switch it on and off and hope that it works. Okay. But at the end of the seminar, please tell me, because that's the only thing I can do. I mean, I can just switch it on and off. There's nothing else I can do.
But I think that it is better. Yes.
Okay.
You were talking for a long period of time enough in order to convince myself that it would be. Probably now it is fine.
Okay. Thank you so much, Adam. Thank you. Okay. Jan, please continue. Sorry about the technical interruption.
Okay, let's continue. So I will present the explicit formula later. So hope there is some motivations behind. And then of course this n minus one q minus one has some interpretations in graphs. We will see in a minute. Okay, then the question will be, how about Unital star homomorphisms from Kunze algebras to its matrix algebra, right? So so we do the similar thing again. So to look at the K theory, so there is a sort of a necessary condition. So like this. So here now, so the K is the size of the matrix, because we know that with Morita equivalence, right? So the MK of OQ has the same K theory of OQ, and the map is by taking the trace. So it's like the identity matrix. When you take the trace, then you have the K copies of the diagonal. So that's why you have a multiple K here. So and then the rest is just similar to the congruence relations, like without the matrix. So here is the congruence relation. So again, the similar question is that assume this congruent relation hold true, and then can we construct like a Unital embeddings from this ON to MK of OQ. So our main result is just to confirm this answer, and then to give explicit maps by using sort of some morphisms at the level of graphs, and apply the functoriality. Like one is the contravariance, one is covariance, and then to obtain this embedding. So actually, I think this project was aiming at provide some sort of concrete applications of the contravariant and covariant constructions developed in Pure and Maurice's previous work. So this 25, this is the contravariant functor. I think it's written earlier, right? So the published later, and then
I think to be honest, it was just a few days ago that I received an email from JNCG that now this paper was physically published, so it has page numbers.
Yes. So
it should be 8026. Yeah, but it really happened a few days ago. Yeah, but it was precisely over there when we reported on how we stumbled upon it. Because it wasn't Kawamura who inspired us. We were playing with so-called locally derived graph construction, which yields contravariantly a star homomorphism. And then Jack Spielberg made us aware that we constructed an embedding of I think it was O2 in M2O3. And this was completely unexpected, but this prompted us to investigate the issue. So this is what I did with Young in Trieste. What happens if I just forget 2 and 3 and I want arbitrary positive, natural numbers satisfying the congruence relation? And this turned out to be not so obvious, but as you will see, we cracked it.
I have a question. So as I observed before, these ON algebras, the system of ON algebras behaves like system of matrix algebras of size n+1. So what are chances that the following could be true? ON embeds in O k+1 tensor of O of k, of Q, sorry.
We have not yet thought about it.
This is an interesting question, but you have to go to higher rank graphs to do it. If you want to do it this way, we did it. Because when you take the tensor product, then we are using higher rank graphs. Whereas when you do matrices, this is, of course, you can also do it using higher graphs, but you can also express it like this. I definitely do not believe that the tensor product of Kunz algebras is a graph system. So that's technology that we are using here is not directly available. However, it would be a good prompt for developing it, if you will. Yeah.
So this means that even in this case, you could find, instead of this realization by graphs, you can use higher rank graphs and obtain different implementation.
Exactly. And if somebody wants to have such a research project as you just proposed, then I will start from the known case, which is solved, see how I can reformulate it in two-graph language, and see if I can upgrade it without, one leg being matrices, but both legs being Kunz algebras. Yeah, that's an interesting question. Yes, because you see, with matrices, you have, if you have a tensor product of matrices, you still get matrices. So that's why somehow this is insensitive, and it's kind of known how you get Morita equivalent algebras by manipulating with graphs. You just attach, a path of a given length to an appropriate vertex, and it changes the graph system algebra into the matrices of this graph system.
Okay, so let me first quickly introduce the definition of a graph C-style algebras. Before that, I need some terminologies about direct graphs. So basically, a direct graph is consists of the set of vertices, right? The set of edges, and with the source and the target maps denoted by S and T. So we also need a notion of about regular vertices. Basically, if you look at the fibrations over by the source map, so if the fiber is empty, so then it's called a source. So it's so if the fiber is finite, so basically we want to, so this regular means that if you look at the fibration over the source map, so the fiber is just non-empty and finite. So that's the set of the regular vertices. So, and then basically I think the graph C-style algebras is about this. So once you have a graph, right? So there is sort of a underlying dynamical system behind it, because you can concatenate the paths to form the. Or you can say you can think of have a point moving along the path of the graph, right? I think the C-star graph algebras catches this sort of this underlying dynamical system. So we have to work with the space of finite paths. So it has so here the label. So there is a natural filtration of the path by its length. So we can project down to eventually to the set of vertices. So if we for the source map, so the steps is basically you cutting the last edge, right? So if you wanted the source map, so you keep cutting the last edge of your path, and then you reach your the vertices as the source. And for the target map, you have to cut on the other end. So I think this is quite intuitive. So I will not say many words about it. So here, so PR usually define this the graph C-style algebras using Levy path algebra. First, I take the shorter cut. I just using this Kunz-Krieger family. So the graph C-style algebra. So given a directed graph E, so the graph C-style algebras is generated by this so-called Kunz-Krieger families. So we have for each vertex there is a projection. So and then for each edge there is the isometry, and then we require that these projections are mutually orthogonal. So, and then with this isometries, it fulfills three conditions. So I think that the first one and the first two often referred as the first and the second Kunz-Krieger relations. And the third one is kind of if the sum is finite, we don't need so the third one follows from the second, right? So the third one, it's non-trivial when you have the fiber over the source map, which have infinite many edges. So we put the third one here. So
may I ask you why you use this ugly definition instead of more kind of straightforward definition provided by Levi's algebras?
So it's just save time. So
you mean the inequality?
Yeah. Okay. Yeah. It doesn't save time because it's much easier to say that projections times isometry is isometry and stuff like this. It's much easier to say than to explain inequality. And you yourself help me to prove the equivalence of these conditions.
Yes. Later, so I think so. I would the last part this part. So this the first relation is kind of an inner product, and we will see some interpretations of these relations in the context of C star correspondence. So so if I have time, so the first so there are many, of course, many examples. So I just presented the ones that are needed for this talk. So first of all, for the Kunze algebra, the graph is this one, So it's a one vertex and n loops on it. So and then for the matrix algebra, so the graph is often referred as the K-line graph. So it's this edge, like V1 to V2, is you can think of this is just the projections mapping the E1, the standard basis of Cn to E2. So and the Q others, and then from V2 to V3, and then this is the projection mapping E2 to E3 and Q others. So and then it's not difficult to show that. So in the matrix form, this is the just standard unit matrix. This is E12 and E21, E23 and E34 until EK minus 1K. So, and then we show that the star algebras generated by this matrices, that's the whole matrix algebra MKC. So it's interesting that so to realize this matrix algebra MK over the Kunze algebra OM, so we just basically we replace the vertices of this EN graph by this K line. So then this turns out to be the graph C star algebra turns out to isomorphic to this matrix algebra. I think so. One of the starting points is that we noticed that this kid, I think so when Pierre was doing some verifications on Blackboard, I was drinking coffee and then we started to discuss, and then so this is so for the basically for the baby case, I think M203, right? So we can directly show that this is we have some explicit isomorphisms, and then the method is it's not difficult to extend to the general like a MK of OM. So okay, first that's the first realizations of this matrix algebras as a graph algebra. So the underlying graph is denoted by GMK. So of course, so at least we don't know any like explicit map to go from GMK to EN, right? So it's so here's the okay, so the general map we want is from ON to to this MKQ with this congruent relation. So I think the first case we did is to put S equal to 1. So in this case, you look at this relation. So I think that's the most difficult part. And then to extend to the general case, you just add a Kawamura embedding. So this is the congruence relation for this Kawamura's embedding. So mapping this OM to OQ. So the difficult part is to construct the Unital embeddings for this case. So okay, so now let's focus on this orange part. So construct the Unital embedding. So here, so we need a bridge. So it's so if we knew some direct paths, if we knew some direct paths from here to here, right? So we wouldn't write this paper, or I wouldn't give this talk. So here, so the bridge is this graph F, M, and K. I think so. The motivation to consider this graph was as Pierre mentioned earlier. So in this contravariant functor construction, he studied this sort of the locally derived graph. So he has some baby model in mind, and after many sort of computations, we fixed the final form of this graph F, M, and K as the bridge. So there, as I just mentioned, there is a sort of admissible graph homomorphisms from F to E, and there is so we will construct this admissible path homomorphisms. So maybe just so the difference. So the main difference is the one is sort of when you pass to graph SISSA algebras. So G is a contravariant and F is covariant. So then you have all the arrows points to the same direction. So you have just our desired embedding from ON to the matrix algebra. So any questions?
Do you intend to explain what you mean by these graph homomorphisms and path homomorphisms?
Yes, definitely.
Okay.
Yeah, the rest of the talk, so I will explain this sort of admissible like graph homomorphisms and admissible path homomorphisms. So and then write down some explicit formulas. So for that. Okay, so basically, so this is outline. So this is basically the proof, except some with this technical part, like what are the conditions required for F and G, and then what are they? So this. Okay, so again, so we started with some terminologies. So a homomorphism of graph is just a map, which sort of basically preserve the sort of the fibrillation structure over the source and the target map. It's map the vertices to vertices, edges to edges, and commute with this source and the target map. So this is the homomorphism of graphs. And for paths, so we're still required. So it maps vertices to vertices, communicating with the source and the target map. And then, of course, it's preserving this concatenation structure of path. So f of p concatenated with q is equal to f of p concatenated with f of q. So So here, so of course this so this is only at the level of graphs, right? But for the graph system algebras, so there are like two Cohen-Krieger relations we would like to preserve. It's I think that's the whole difficulties here, right? So it's so first I would like to explain the covariant construction about the covariant looks like this F. So there are some technical conditions. So this injectivity. So when you restrict on fibers, it's all over the. I think so when you restrict it on fibers of the target map is injected, and then this monotonicity is just if the range, the image path, they are compatible. The pre-image parties, they are compatible as well. So for the.
But you should explain what comparable means.
So comparable means just one path is so it's like there is a smaller one inside a larger one. So that's the intuition. So it's so one is a part of the other, the large one.
Yeah, but it's quite crucial because there's an ambiguity. I can write, but what I write disappears. So basically, we say that alpha is less than equal to beta if there exists a gamma such that you can write beta as alpha gamma. And this is important that you extend to the right, okay? Because when you just say that one is bigger, you don't know from which side.
Okay.
And it's important
yes.
that you extend to the right, okay? And then comparable means that either alpha is less than equal than beta or the other way around. And if in the image two paths satisfied, then they have to satisfy in the domain. Which means in particular that if you restrict yourself to edges, okay, one edge extends another if and only they are equal. So kind of you get here injectivity of edges as a result of monotonicity.
Okay. Yes. Thanks for the remark. So this can be extended at two ends, but our convention is so one path is smaller than the other. Is like we extend from the right end. Right? So that's some subtlety here. So. Yeah. So, I think
it still doesn't mean that the map itself is injective, because you can map a loop into a vertex. And then you have infinitely many paths, right? Because you can wind around the loop as many times as you want. And all of them are mapped into just one vertex. So by all means, I'm not saying that path homomorphism must be injective. However, you must be injective on vertices, which is kind of obvious because these are mutually orthogonal projections, so they are part of a basis, so you cannot identify them. So injectivity on vertices is obvious. And monotonicity on edges, I mean, that's, because comparable means, of course, if two paths are equal, then they are comparable. So then this means that the edges would have to be comparable, but this means that it would have to be equal. So you get the injectivity on edges if they are, mapped to, if they are mapped to comparable paths. But it might. So okay, I think I said it incorrectly. Because if you can have edges which are mapped to non-comparable paths, and then you cannot conclude anything. Okay, sorry, it's a bit more tricky. Yes. Okay.
Yeah. So what you mean is that injectivity is not a consequence of monotonicity applied to some class of.
Yeah. No. I forgot that. You might simply map edges to paths that are not comparable.
Okay.
Your slides vanished.
Yeah. It will come back in 1 second. Okay. So I think the most difficult part about this covariant construction is the regularity. So I think so. Maybe I can try to show. So this is sort of the technical version of the meaning of regularity. So it's I think it's it's rather technical. I would not to explain like step by step in this talk. So the sort of the plain English version is the following. So let's fix a vertex. So and then look at how to map the fibers over the source map to the other side, right? So the image of this fiber has the following structure. So you take an edge, either you set it as a length one element, and then if not, if you want to extend, but you have to add all the edges emitted from emitted from the target of this X. Sorry. So and then you have to keep iterating these steps. So once you have the length 2 elements, if you want to grow the length, and then you have to add all the edges emitted at the target of X. So here it's best to show an example what's the meaning of this extended by all edges. So I think the best example to explain this is to use
Sorry, I have a question.
Yeah.
Could you explain why paths of length 2 play this distinguished role?
No, I don't.
Oh, it doesn't.
So,
I mean,
you have a condition on.
No, it goes on. You iterate it. Can you have length medium?
So just let me show you. Yeah, let me show you this example.
Paths of length 2. I don't understand.
What Yang is saying is that okay, you have a bunch of edges emitted at your regular vertex. It's a finite non-zero number, and you have at most as many edges emitted at the image of this vertex. Okay. So now, in order to really see what is the image of a set of vertices under your map F, it has to satisfy certain rules, which are spelled out there, like a legal statement. But the essence is reverse engineering for the second Kunstkrieger relation. That's it. And this is why the basic rule of engagement is that if you choose to extend some edges, you say, okay, I take a bunch of edges and I don't extend them. Fine. But what do you do with remaining edges? Well, you extend them, but the point is that you have to extend them absolutely by all edges that come out from the endpoints. But then you can iterate. You can keep a bunch of paths of length 2, and the rest you can extend to paths of length 3, and so on and so forth. And finally, at the end of the day, you will get as many paths as you have edges in your source graph.
Okay, so this was the base of this recurrence.
Yeah.
Okay.
Yes, exactly. Yes.
Okay.
Yes.
Okay.
Yes. There is another way to explain it, which we were forced to employ when trying to understand relation morphisms between graphs and when doing this extended path homomorphisms. It can be said as follows, and by the way, it's important because the combinatorial embedding, not embedding, it's a combinatorial representation of a second Kunstkrieger relation. It's not just sufficient, it's necessary. It's basically equivalent to the second Kunstkrieger relation in a way. So it basically goes as follows, that if you start again from a regular vertex, okay, and then you look at any finite path stemming from the image of this regular vertex, then there always exists an edge which comes from the source regular vertex that is mapped to a path at this image regular vertex to a path which is comparable with any path that you choose. So somehow, by all means, if you take the image of all edges, you will not get all paths that are emitted from the image irregular vertex, but all paths that are emitted at the image regular vertex are comparable with one of the paths, which is the image of an edge. So that's another way to explain the regularity. And it's really remarkable because it's equivalent to the second constructed relation. Equivalent in that sense that if you have a morphism which satisfies the previous relations, okay, so it induces a homomorphism between concave algebras, or if you want step-with sister algebras, then this induced algebra homomorphism preserves the ideal generated by the second constructed relation if and only if this relation is satisfied. And for us it was very pivotal because it's very, very hard to prove that regularity is composable. So regular composed with regular is regular. This is hard to prove. In this paper with Mariusz, we did it by hand, but this was ugly. Whereas in these more recent papers with this new formulation I just told you about, we use the fact that it's equivalent to preserving the ideal generated by the second constructed relation. Then, of course, if you preserve an ideal here, preserve an ideal there, then the composition of maps preserves the ideal. And because it's equivalent, we know that the regularity condition is composable, so admissible morphisms, admissible path homomorphisms form a category.
Okay, so probably let me just quickly explain the first part that just Pierre just said. So just to give a sort of an intuitive way how to derive this Kawamura's embeddings. So recall that to have an embedding from OM to OQ, we have this congruent relation. So M minus 1 is equal to some multiple of Q minus 1. So let's take this example, say M minus 1 is 3, Q minus 1 is 1, say Q is 2, M is 4. So basically the rule is that as I mentioned, so when you extend the path, you have to add all the passes like emitting from its target. So here so to use this is basically you think about first of all you think about what's the maximum length. So basically I want to assign these m edges right to some path to m paths on this side, right? So with this we see that the m is so basically you think of what's the maximal length you can have. This m minus 1, there is minus 1. The 1 refers to a special path which is max to the maximum length. So say I call this path En. So it will map to have the maximum length. So it's like this. Okay. But on the right hand side it's a loop, but because I want to emphasize the length, so I would just writing like this. So by the rules that so if you want to here, so here's the restriction, right? So once you extend, you have to add all the addresses from here. So 1 and 1 and 2. So this is added 1 and 2. This is so here. So from this by this counting, because you have to add this part of addresses, you can see that the length cannot. So it has to be S. The maximum length. The maximum length is equal to S. This S is this multiple. So here S is equal to 2. In this case, S is equal to 2. So because of adding this, you cannot have more. So once you figure out, and then by adding these edges, then you can see that already So there are already n minus 1 because of these congruence relations. So you divide it by this n minus 1 by SS batches. So from here. So from here. So from here. So I think that's the. So then you have the morphisms. So is that a kind of clear? So basically, once you want to extend, you have to add all the addresses emitted here. So it's a so then this gives you the once you write down using the so I have to clean this. So of course, so this minus 1, this special edge here is just means you have only one maximal length, right? So here you keep counting this this 1 in the. So that's why you have this minus 1 here. So okay.
And it's maybe worth emphasizing that here this regularity condition leads you directly to the formula of Kawamura, because if you are facing, how to map m loops into paths based on n loops stemming from one and the same vertex, and you want to preserve these rules of the game, you have only basically one obvious way to do it. So this is what I enjoy about it, because we guessed the formulas for Kawamura before reading them, because they're dictated to us by the regularity condition.
Yes, it's dictated because you figure out that there's one maximal length, and then at each one, so you have to add all the edges emitted here, and then you by counting, you said has to be all this. So then you already have enough number of edges for the image. So so the rule is fixed in this in the process of constructing this Kawamura embedding. So it's fixed. So it's okay. So I hope this gives you some intuition, like about the remark. Like once you have extended some edge in this image, you have to add all the vertices. So I add all the edges emitted from these vertices. So okay. So let me just clear this mess. So back to yes. So this is the explicit formula. So you can I just explain. So it's written down in Kawamura's paper or our preprint on archive. So once we have the map at the level of graphs, is the morphisms between C-star algebras is straightforward. It's just map the generators, this P to corresponding like the generators of FP. So this sort of this functorial construction is straightforward. So but yes, the tricky part or the difficulties resides in this regularity for this covariance construction. So any questions? Okay, so let's move on to the contravariant.
Excuse me, may I have a question?
Yeah.
Well, he just asked you if you want to ask a question. So he just asked you if you want to ask a question. So go ahead.
A real question.
Yeah.
Oh, okay. So could you come back to this F lower star above?
Yeah.
Yes. So this you are considering paths of length 0 and 1. What kind of induced maps for paths of higher length you obtain?
I mean, just have concatenation property, so it's uniquely.
Yeah, we are extending. Yeah, but
No, FP is not actually
arbitrary. No, not arbitrary.
No.
Because you have something in infiltration one.
No, FP is not length
yeah, but you can map an edge into a vertex. So if its edge is a loop, and it has to be a loop then, okay? So you can map a loop into a vertex, and then you have infinitely many paths, which are all looped to any power, we are mapped to under the same vertex.
Yeah, but what kind of structure on paths is preserved by this kind of maps whose images are of restricted length?
Well, here none. I mean, nothing obvious. That's we just have to respect the concatenation. That's all. And be injective on the vertices.
Yeah, so they are not arbitrary mappings between paths.
No, the mapping requires.
He gave a definition
it is generated from 0 and 1.
Yeah, okay, so as Mateusz mentioned, you can view it in the following way. If you look at the graph as a small category, in the sense that vertices are objects and finite paths are morphisms, then this is just a function.
Okay.
So thank you, Mateusz.
Like it better.
Okay. Now, I only say this remark when I give this talk, but this time I got bored by saying it over and over again. But yeah,
this is a good definition for it.
Yeah, sure.
Good. Okay.
Yeah, if you want to explain it to a child on the street, this is the best one. It's a fact.
Okay, so this is the constructions of this covariant function. This covariant functorial construction. So let's move on to the contravariant side. So for the contravariant side, so we start with just a graph homomorphisms. It's like preserving the length. So we map vertices to vertices, edges to edges. So here, let me go full screen. So here are the technical conditions. So here is some properness. The map between finite path is finite to 1, and so the target bijectivities. So and then the pre-image regularities. So the pre-image regularities is the map, like the pre-image of the regular vertex is regular because of the second point relations is stated for the regular vertices. So it's that's why somehow you need this pre-image regularity. So here a geometric interpretation of this target bijectivity is just the pullback regarding the fibrations by the target map. So it's so target bijectivity is saying that so E1 is the pullback with respect to, so here F is the morphism, map the vertices to vertices, and here's the target. So regarding the target map, so E1 is the pullback bundle of F. So that's the target bijectivity. So
sorry, I have two objections. Why on earth do you use this symbol of a tensor product, not just the Cartesian? I've never seen it.
It should be Cartesian.
It should be Cartesian.
Typo.
It's times, not all times.
Thank you. Typo.
Yeah.
Typos.
And also, I don't see any reason to capitalize B here.
So here, sorry, it's not tensor. It's cross.
It's cross. Yes.
It's cross type.
And here it should be lowercase here.
Oh, so yes, lower B, the bijective.
Yeah.
Lower B. Yes.
But if you allow me, let me add a little bit about these graph homomorphisms, because somewhat unexpectedly, although it's obvious from hindsight, you can easily classify all such graph homomorphisms, and basically it comes from what you just explained, from this target bijectivity. So if you want to construct absolutely any admissible graph homomorphism, but basically, and your target target graph is fixed, take any graph, and then in order to construct such a graph homomorphism, well, you can choose any set theoretical map from your new vertices to your old vertices. However, there must be a restriction that, of course, it's proper, and it must be the image of a source map must be inside the image of F0. Okay, so this is one restriction, and then arbitrary map is fine. Okay. And then edges must be this fiber product. You have no choice. So basically, all of that you have here, you can take any bijections from this set to itself, and this would give you all possible targets and maps between edges. And then the only freedom that you have is the way you lift the source map, which is given to you by the axiom of choice. And absolutely any admissible graph homomorphism of that source. There's also a regularity condition, just very simple, that pre-image under F0 of the image of the source map is contained in the image of a source map for E, and that's it. Any admissible graph homomorphism must be of that form, so it basically boils down to a choice of a nice proper map, a lifting of a source map, and any bijection of the set of compatible pairs given by this book. So this is quite incredible for me, that absolutely any admissible graph homomorphism is of this clear-cut form.
Okay, thanks for the remarks. So let's go. So let's look at an example. Oh, okay. So before before going forward, I need to tell you what's this contravariant functorial construction, right? So once you have such an admissible graph homomorphism, so basically, so here, so it's like you think of so this comes from that you are dualizing the pullback bundles to the level of functions. So that's why you have this summing over the G inverse, the pre-image. So that's the way how to map the generators to other set of generators to obtain the C star homomorphism. Okay, so this is the example will be the G map in our main in the proof of our main results, right? So we need we have a graph homomorphisms between this F type, Fm and K to this En. So this is the graph for Kunze algebras. So the rules are just very simple. So here, since you only have one vertex here, so there's no choice. All these vertices collapse to the single one. So the point is how to assign the edges, right? So basically, you break this down so as the fibers of the target map. So here, so you will see here each one by very simple counting, you will see each one has the same number. So each one has n edges in here because of so in this graph each red arrow represents n-1 edges. So here you see there's n incoming edges, like n incoming edges at each vertex. So then so the rule is to say that all this batch of n edges is just mapped to this n edges. You can choose whatever bijective map that will work, right? So the way is so the rule is dictated by this one, by this map. So why you look at these targets, right? Why you look at these targets? So it's so this map will detect you to look at all the maps like incoming at this vertex and map them to the edges of Conte algebras. So any questions? So this is the graph homomorph admissible graph homomorphisms. So from F to N. So okay, so the last part, so for our main proof is to oops, I was trying to go. So maybe it's so annoying. So I have to share it. So if I want to jump forward and backwards on slides, I cannot use the presentation mode. So I will just, because I would like to do some jumping here, let me just enlarge this as much as possible. So, okay, so far, so I've constructed this map, right, to arrive at here. So the last step is to construct this admissible graph homomorphism F. So to complete the proof. I think by the time I think Pure left Trieste. So at that time, so we only know that so there is a so we did this at the beginning by computing the K theory. So we computing the K theory of this graph SISSA algebras, and then to show that it maps like identity to identity. So then there is a higher level result at the K theory. So with such a assumptions, such conditions, there is isomorphisms between these SISSA algebras. That was what do we then this graph F and then must be the correct one. So that was the knowledge at that time. So but now I think so by Piot's other projects, so we have a very nice way to construct explicitly what's the map from this FMN to GMK. So by so-called moves. So
let me weigh in for a second. So first we have a typo here. There should be K. It's FMNK, right?
Yeah.
And as you nicely put it, this graph on that slide is a bridge because we had this rose petal Kunz graph, okay, for ON, and it was kind of clear to us what is the graph of matrices over Kunz. But we couldn't construct any admissible graph homomorphism between these two graphs. So this was a drawback. And then we realized that in order to have such an admissible graph homomorphism, as you explained, we need to use this graph, and it works. But then how do we know that these are matrices over Kunz? It's not so immediately obvious, okay? And just as Jan was explaining that for this class of sister algebras, we have a nice theorem saying that if K groups agree, then we are Morita equivalent. But if K groups agree and also the classes of one agree, okay, inside these groups, then we are isomorphic. And of course, given a finite graph, computing K groups is completely trivial. You have it on the plate. It's one of a raison d'etre of graph sister algebras. But to find a class of one in K0, because K1 here vanishes, is a bit of a burden. It's of course, it's all high school mathematics, but it's a linear algebra over integers, okay? And you have to do some gymnastics to to really prove by classification, if you want, that this is indeed matrices over Kunz. But then, if you just do it by classification, you don't have an explicit map. Yeah. And at the end of the day, we want to give you a polynomial formula embedding Kunz into matrices over Kunz. And this is why now we go to the next part, right? That not only we know by classification that these are they give you isomorphic graph sister algebras, but by employing the celebrated shift move, which everybody knows and enjoys, you can actually, by iterating it, construct explicit isomorphism from here to there.
So yes, one of our slogans is we want explicit constructions, right? So that's why we are not just quite satisfied with the existence isomorphisms by the K-theoretical results. Okay, so yes, Piotr just explained. So we needed this shift move. So to construct this admissible path homomorphisms, let's just explain what's the shift move. Basically, the shift moves will give a sort of the shift move will induce a admissible path homomorphisms, right? So sort of the large idea is that we want to. So we have some sort of general descriptions of what are the properties for this admissible path homomorphisms, right? So it would be very nice to have some basic constructions to produce some examples of this admissible path homomorphisms, and then somehow, so in general, we just compose these basic steps, right? Iterate all those basic steps. So that's the general thought. So one of these basic type is the celebrated shift move in here. It's very easy. So you take two different vertices of the graph E. So here you choose it. So let's look at the B. So here you choose. So you need an assignment and injection from the fibers over the source map at V to fibers of the source map at W. So that they have the same target here. So that they have the same target here. So and then you can just remove a bunch of this.
But you should really emphasize that this vertex V or U is regular. It's important. It must be a regular vertex. It cannot be an infinite emitter, whereas W can be an infinite emitter. You don't care. I mean, obviously, if you want to have an injection, W must emit at least as many edges as V, all right? But it can be an infinite emitter. You don't care. And also, you do not assume that there are no loops. I mean, you can have an edge which goes back to V.
So yes, I think the operation, so to produce this graph is just okay, you remove so you select a bunch of edges. Let's say this say one. So for simplicity, so you remove the image of this edge and adding one formally xw coming from W to V. So change the direction. So you remove this one from V to W and adding this to W, adding one from W to V. So this new edge will be we call the X. And then to construct this admissible path homomorphism at a level of graphs, you just insert this new edges in front of this.
So allow me to draw a picture.
Yes, the picture is a very.
Yeah, but it's already very. This is already. Can you go back to up?
Yeah.
Because I want to give a generic picture. Very simple. So here is your V. It emits something. Here is your W, and it must emit an edge which meets with this one at the target. Okay. And then basically what you do, you say, aha, And now I put this extra edge X from V to W, and I replace this edge by this path of length 2. That's basically what you have to do. Okay?
Okay. So yes, I will repeat what Pierre just said. Okay, let's look at this. So we want a map from this F to G. Okay, so basically look, what we want to move all the red edges is landing at the different vertices to V1. So here the first step I take this part. Okay, I take this part. So here is the theta map. So if you look at, I take it, this will be your V, this will be your W. So here there is only one outcoming edge, right? So the theta, so the domain of the theta is only at one edge. So you map to one of this, okay, and then by the shift move, you can move this one, remove this one, so now it becomes n minus 2. Just cut it and adding one x, here, the blue one, right? Going from W to V, right? So in this one step, you move one red edge to which is a loop here to landing at the V minus k minus 1, right? So now by iterating this. So you can remove all these edges here. So now the graph look like this. Now there are n minus 2 edges, right? So now to move this to another vertex is just the same story. So you look at this V, and then you look at this as your W. So because they are landing at, so this is your the domain of your theta. You map to one of these red edges, right? So by the shift move, you can replace this one by a blue one. So now so this is n minus 3.
It should be 3. Yes, minus 3.
N minus 2, n minus 3. So one less becomes the blue one. So and then you do it n minus 1 times. So then basically the red edges, they're all gone, they all become blue. So now basically, so you iterate all this process, right? So so first we move the red one to here, and then to here, to here, to here. So eventually all these edges, they landed at V1. So that's the morphisms for this F. So of course, then you have to apply this functorial construction, translate the moves to the formula at a level of SISSA algebras. But that's straightforward. I will not explain that. So any questions? So that's sort of kind of a complete our main proof here. So.
Well, what I'm missing here, I mean, it should be somehow emphasized. Could you go up to the previous slide? I mean, of course, it's very important that it is an admissible path homomorphism, but so it induces a star homomorphism. But what everybody knows who does moves is that it's an isomorphism. Okay, it's an isomorphism, and it is unital if your sister orders are unital, but it's not gauge equivariant, because you map an edge to a path of length 2. So you do not preserve the gradient, you do not preserve the gauge action. Yeah. So it's important that we know that the covariantly induced star homomorphism is necessarily an isomorphism, which is what people who do moves know very well because they invented it.
Okay, so any questions so far? Okay, so I think I have about 15 minutes, right?
Yeah.
So okay, so now I have some time for the final, for the last part of it. So okay, so yes, I would just want to share some lights on the, especially on on the technical conditions about this this path homomorphisms and graph homomorphisms. Something like this one, and something like this target bijectivity. So where is my target bijectivity? Oops. So okay, let's just jump to the last part. So the last part we start with to construct graph C-star algebras using in the framework of C-star correspondence. So maybe this part I can go through. Put in presentation. So let's move on to something analytic. Just let's recall some basic notations. So what is a C-star correspondence? It's a module over C-star algebra A. So I think the quite informative part definition is it's a right Hilbert A bimodule. So it's a right Hilbert module. So it means that you have an A valued inner product fulfilled in the standard property of these A inner products. So for the left module, for the left action, we require that the left action of A on X represented as adjoinable operators, because so in the setting of C-star modules, instead of of operators on Hilbert spaces, right? So the adjoint property is not guaranteed. So we usually consider like adjoinable, this L of X adjoinable bounded operators. So what's the notion of compact operators? So here is because of the existence of this A valued inner products, so any element in X has two rows, it has an element in X or has something dual because using this inner product. So then we form this sort of the analogy of the rank 1 projections in the Hilbert space setting. So here you have this the form like a theta xy. So by viewing X as an element of X and Y using its dual role, so this is an operator, adjoinable operator. So the adjoint is just you flip this Y xy. So and then the closed spans of this forming ideals, the analogy of compact operators. So this is so example. So for a graph, so how to construct a correspondence. So basically, so you have a bimodule. Right? So for the right model, right Hilbert module, so we use the range map, the target map or the target map. So of course, so given this is your C-star algebra. These are functions on. Sorry, this is a typo. This is the functions on vertices. So 0 is like vanishing at infinity. So if you have an infinite many vertices, so 0 means vanishing at infinity. So C here is like a compact support. So basically you are consider functions on. So for functions on vertices, you use the range map. So using the pullback, you get a function. You get a function on the edges, and then you use the pointwise multiplication. So that's the right action in here. So the inner product here is defined by integration over the fiber. Integration over the fiber in here. And then, of course, the left action will be defined using, instead of the range map, you use the source map. In short, so you use the range map for the right action, and the inner product is given by integration over the fiber. So in particular, for the action, for the left action, so I will use. So I think this formula is kind of useful. So let's use the 1b just to denote the characteristic function on this single vertex v. So when this because we are consider left action, we are using this fiber over the source map. If the fiber is finite, we can do a sums. That's the standard pullback map, right? So it's not pullback map, dual map, like dual of the source map. So here, so it acting on functions on edges using this sort of this standard finite rank operators in here. So
by the way, there's a type.
Yeah.
Where? It should be C0 of E0.
Yes, I mean here. Yeah, type this is on 0. Yes. Okay, so this is the correspondence structure. So here, so given your correspondence, you can construct so-called representations or like Toeplitz representations of the C star correspondence. So basically, so you're gonna map them into some other C star algebras, while all this bimodule or like Hilbert module structure, they are preserved. The inner products and the bimodule structure, they are all preserved in the correct way. So by the way, I think the crucial part is the second and the third. So the first one can be derived by the second one. It's basically, you look at here. So once you have an operator of S star times S or something like that, so it's an inner product in this way. So and then for the left actions, you can factor it out. So basically, so a representation. So there are two levels. At the level 0 is the functions on vertices. At the level 1 is functions on edges. They are all maps to some C star algebra B. So you think of the B as some subalgebra of some subalgebra of bounded operators of some Hilbert space, and then it becomes an operator. Right? So we keep using B as some flexibility here. So here is the assumptions to preserve the structures or in the definition of being C star correspondence. So any questions? So probably I should give examples.
Yeah, I have a question. What is the relationship between your first part of the talk and these correspondences? I'm completely lost. Why are you talking correspondences right now?
Okay. Because so the graph C star algebras can be constructed out of correspondence as a representation as the universal representations of correspondence. So basically, once you have a graph, you form the correspondence, right, using the range and the target map, and then you look at the universal, some universal one, and then the universal one gives you the graph C star algebra. So you will see in a minute. So now how this structure translates exactly to the Cohn-Krieger relations. Okay. So now let's take this correspondence. A is the functions on vertices. X is the modulo X is functions on edges. So for any representation, like landed in some other C star algebra B, so you denote by the projection is just the image of this characteristic function. So you said this and the S is the image of tau 1. So and then you have a family of projections and isometries that fulfill the first Cohn-Krieger relation in here. So you can check. So first of all, these are mutually orthogonal projections. So I forgot to mention. So tau 0 should be a star homomorphism algebra. Star homomorphism is preserve the star structure and a multiplication. So tau 1 is because X is just a module. Tau 1 is just a linear map. So so here, because tau 0 is a star homomorphism, so now the image is just they are mutually orthogonal projections. And then if you check the inner product, write down the inner product here. So it's exactly the first Cohn-Krieger relation.
By the way, why do you write CC over here instead of CO here?
So CO is the function vanishing at infinity. CC is the compact support.
But
So
your topology,
but
your topology is discrete, so it's the same.
Yeah. So I mean, for us, like for the examples I showed before, these topological conditions do not play a crucial role here. But if you go in general, so of course the topology matters, right? So here, okay, the story is here. So it's like you have a graph, you constructed the so-called structures of correspondence, means that you have a bimodule and an inner product. The inner product is compatible with the right action. So where it's basically the right action as acting as scalars with regarding this inner product, while the left action acting as adjoinable operators. So so once you have the representation, means that you map them both this algebra and the module into some C star algebra, right? So that all these structures are preserved. Now this inner product structures basically gives you the first Cohen-Krieger relation. So that's the point. So and then the third is kind of obvious. It's not important. So okay, so now basically the first Cohen-Krieger relation is encoded in this structure of representation of a correspondence. So that's the first story. So what about now the more subtle part is about what about the second Cohen-Krieger relation, right? So the Cohen-Krieger relation comes in the following way. So first of all, so Cohen-Krieger relation is defined on regular vertices. So we kind of need a notion of some functions. So here we consider functions on all the vertices. What about functions supported in the set of regular vertices? So how to find them using some analytical language. So here it's kind of straightforward. So consider this the characteristic function of some vertex. So Vx is the left action, right? So if this is in the kernel of the left action, it means that the fiber added by the source is empty. It means that the vertex is a source. So this operator acting as a compact operator, if and only if the source has finitely many elements. So that's the description. So if both are fulfilled, so then the V is a regular vertex, right? So this leads us to consider the following idea, denoted by Jx, in the following way. So it kills by functions. So which is so in the graph setting. So these are the kernels are functions supported outside the regular vertices. So and then the phi of x is in the compact. So combine this. So this is a sort of a way to describe functions supported in the regular vertices, which is an ideal in this algebra. So this definition works for general like analytic setting. So but in the case of graph correspondence, it's just single out the idea of functions that's supported inside the regular vertices. So okay, so now to come to the second Cohen-Krieger relation. So
now you have another typo here.
This side, this one.
Yeah. Off.
Thank you. So should be removed. So here is the comma here, tau 0.
Yeah. Okay.
Okay. So given your representation of a six-star correspondence, so because it dictates a map. So originally it maps to tau 1 sends x to b. So because of the inner product elements in x, so play the role of itself or as a dual function, right? So that we form this finite rank operators. So theta xy. So tau one. So using tau one, it induces star homomorphism on compact operators. So to map all the compact operators to B. So by this formula. So basically, the second Kuhn-Krieger relation comes in the following way. So it's a so whenever A is in JX in the language of graph, it's that a functions that are supported in the say A.
You've muted yourself.
You muted yourself. But I didn't this game. Jan, you are muted.
Oh, it's something worse.
Here, can you hear me?
Yeah, now we can hear you, yes.
Yeah, so somehow I have to jump among slides. Sorry.
Yes.
By the way, your time is up also.
So okay, yes. So maybe just 2 minutes to complete to finish the story. So it's a so the second Kuhn-Krieger relation encoded in this covariant, they call the covariant condition. Basically, so the left action acting at a compact operator, which can be mapped by this induced map. So that have to be agreed with the original representation in here. So that's the because let me, you see immediately. So by applying the settings, so here, so the original representation mapped the characteristic function to the projection, right? So and then so the left action is given by this formula. So and then after the representation of the induced representation tau delta, it's the summing of this isometries. So this is exactly the second and the Kuhn-Krieger relation in here. So long story short, so basically, what's the Katura's argument about this contravariant functorial relation? It's basically so let me jump to the final remark in here. So the point is that so a graph homomorphism gives you a pullback diagram, right? So E1 is the pullback S, coordinated fibration. So because when you pull back bundles, so you can also pull back the sort of the measures. So the inner product is defined by integration over the fiber. So basically these target bijectivity conditions implies the sort of the first Kuhn-Krieger relations about, and then
yes,
for the second
Kuhn-Krieger relation, yes,
it's relatively easy. You just need this map G0, like the preimage of regular vertices is also also regular. So it's so basically, so here for the contravariant construction, the target bijectivity guarantees the sort of the inner product structure, or also the whole correspondence structure, while this preimage regularity guarantees the second Kuhn-Krieger relation. So, but for the covariant functor, it's much more complicated. It's much more involving. You have to work with the finite path, the correspondence of path, which I don't have time to explain. So I'll just stop here.
I don't understand what you mean covariant property. Sorry, I really don't understand.
Oh, covariant property is this one.
Covariant representation. Okay.
Covariant, yeah.
Okay. Okay, thank you. Yes.
Yes. So yes. So the second Kuhn-Krieger relation is encoded in this sort of a covariant property of the representation in here. So that's also just one quick remark. That's also explained. So in the contravariant construction, right? So we require that. So when you record that in the remark, right? So the conditions when you extend your edge, you must adding all the edges. So emitting from the targets, right? That's sort of a compatibility with this left action, which use the dual map of this projection. So now in the path algebra case, you have the projection from path length of length n to path of length n minus 1, right? So an iteration, right? So it's a sort of the remark I gave before is somehow some compatibility with respect to this projection by dropping the last edge of path n to get a path of n minus 1. So okay, that's all I want to say. Thank you very much. Yes.
Thank you.
Thank you.
Any further questions? All right.
Yes, I have a question. So the second part of your talk was suited well for topological graphs.
Absolutely.
Yes,
So
it's the language of topological.
How much? Yes, this is the natural language for this context. So, what parts of the first part of your talk can be extended to the context of topological graphs?
So let me answer this question, if I may, because you mentioned the name of Katsura, and in fact, Katsura found these admissibility conditions several years ahead of us, and in the context of topological graphs. So when you look at admissible graph homomorphisms, they were unraveled by Katsura, several years earlier in the context of topological graphs. So here we really have it in full generality for topological graphs, and we take Katsura's conditions with discrete topology, you get on the nose of the definition. Okay, so that extends automatically, and I'm wondering if we have a similar classification property for topological graphs. It should be because there's target bijectivity also is over there in some topological form, and that's completely unexplored because just like us, Katsura just took this element-wise direct formulation of what target bijectivity means, whereas the conceptual understanding is given to you by this pullback property. That's the way to look at it. But this avenue, as far as I know, was not explored. Although, on the other hand, the reason why we knew about this pullback formulation is because Mariusz was working with John Quick in Arizona, and John Quick in his, I don't know, maybe Kunz, Bimsner, whatnot, was using this pullback property. So Mariusz was aware of it. In bigger generality, you should use a pullback diagram, and then you can quickly prove that target bijectivity is in fact equivalent to the pullback property. But I don't know. I don't think that this is completely explored in this context of topological graphs. But it should not be a big deal.
Yeah.
Although,
what I just explained is just basically it's some small part of arguments in Katsura's paper. So yes, Katsura found this. I think because like as Pierre mentioned before, so their work somehow to sort of reverse engineering of this algebraic version of these two Kunz-Krieger relations, right? So for Katsura, so it's they put this the two relations in the language like this, like a covariant condition, and in the language like preserving this inner product structure. So then it's for me it's somehow it hits like once you have the pullback, right? So it's you pull back bundles, you pull back the measures of the fibers. So the pullback is the natural notion somehow give you when you do in a contravariant way, so to really preserve this inner product structure. So that's Yes, that's some learning from Katsura's paper that I have so far. So it's
yeah. In fact, I was asking about this unital embeddings. How to see these unital embeddings in classes of sister graph algebras for topological graphs. What is happening? So, if I'm not mistaken, so this first theorem was of Kawamura.
Yes.
Yeah.
That's not Katsura.
Yeah. So this my question was about marrying. Okay. Kawamura is Katsura.
But in what sense? You want to have? I mean,
how the technology of these topological graphs could be transported to questions about unital embeddings, but in the realm of graph system algebras of topological graphs.
Well, for starters, we don't have, as far as I'm aware, a topological graph version of admissible path homomorphisms.
Oh,
so that part is missing. Okay. And secondly, I know this is the work of my current and former PhD students, Mariusz Tobolski and Artur Gothe, where they really got some very beautiful pullback construction using topological graphs. You see, and it's related to the non-commutative CW complex structure of Waxman-Soibelman quantum real projective spaces. And then, one case is easy, one case is more complicated. Odd even dimensions behave differently. But to cut a long story short, at a certain moment, you need to put in the sister algebra of a quantum odd ball. And quantum odd balls of Hong-Szymański are not graph sister algebras. But what Mariusz and Artur showed, that they are topological graph sister algebras, and they managed to explain this non-commutative CW complex structure of quantum real projective spaces using topological graphs. Okay, so this is where I have a concrete application into non-commutative topology of topological graph sister algebras. But you see here, this motivation was kind of coming from these specific simple sister algebras like Kunz algebras. And I don't know of any such interesting objects in the realm of topological graphs. Okay. What do you get over there? Do you have some interesting embeddings? Yeah. Okay. Here, the problem that we solved was directly related to, if you want, the classification of some simple sister algebras and morphisms between them. Here, this was this classification theorem that says that if it's allowed by K-theory, it exists. So you can always lift. That's remarkable. In fact, this is part of a game when you do Elliott's classification, is that you lift, because Elliott invariant is given by boosted K-theory. Okay. So somehow the way you prove that Elliott invariant classifies sister algebras is that you take this morphism between Elliott invariant, you put K groups in particular, a bit of and some other stuff as well based on K-theory, and then you can lift it to an isomorphism of sister algebras. So isomorphism of these invariants based on K-theory lifts into isomorphism of sister algebras. So here we are kind of doing it in the same spirit. We are no longer talking isomorphisms, but homomorphisms, okay? But we are saying, all right, there is a homomorphism of abelian groups that are K-theory groups, and this homomorphism of abelian groups preserves the class of 1 in K0, then it means that there exists an honest, genuine star homomorphism between sister algebras. And we now answer the question, okay, can we construct it? Because by far, obvious, if you look at things like Jianshu's sister algebra, then you have this famous construction, but then you can also construct it using some nice foliations. And we cannot prove directly. You prove by classification that SISSA are isomorphic, but there is absolutely not even a hint of how it can be implemented. Just know it exists, but it's not constructed.
So from what you said, I understand that these constructions work well with limits of algebras. And the question about this unital embedding is something like what? Is it similar to limits or the co-limits? I don't know. Okay, maybe it's a different story.
Yeah. But since you mentioned Unital, let me emphasize, and again, apologies to the experts who know it by heart, that when you look at contravariant factoriality, this formula given by a sum, then you always preserve a gauge action, you preserve a grading, and also if your sister algebras are unital, then so are your star homomorphisms. Okay, but when you go to a covariant factoriality and you turn an admissible path homomorphism into a star homomorphism, then it not only that it just violates the grading, it's not gauge equivariant, but also it need not, it might, but it need not map unital sister algebras to into sister algebras. And the most obvious example is constructing compact operators out of matrices. You enlarge the size of the matrices, you have these non-unital embeddings of matrices into bigger matrices, and it's implemented by path homomorphism. But of course, it's not unital. It cannot be unital. So it's important to bear it in mind. And maybe to a final comment is, you see, when you look at the formula for star homomorphism given by a path homomorphism, then you see that these are monomials, but of arbitrary degree, because you can map your edge into path of any length. Okay, so you map a generator into some multiplication of other generators given by edges. Okay, but when you look at the formula for a star homomorphism given by an admissible graph homomorphism, well, then you always preserve a degree. So a generator goes to a generator, but you allow sums. So you have a generator going to a sum of generators. When you combine the two, you obtain a polynomial formula, because you allow sums and you allow powers. Okay, so that's why you can claim that basically that basically we have a polynomial formula embedding any cons algebra into matrices of a cons algebra as long as the congruence relation is satisfied. So we construct explicitly such an embedding Kawamura style given polynomial and generators for this slightly more complicated situation using graph theory. So that would be my summary of that result.
I have another question.
Go ahead.
More concrete. If you have mappings, algebra maps between matrices, okay, matrix algebras, then you don't only have this condition for the existence of this map, but you are controlling exactly what's the shape of this embedding, this block structure. Okay? You have very explicit implementation of your maps in terms of graphs. So my question is, can you control this block structure of this embedding? What can you say about the shape of this embedding, the image of this embedding inside of these matrices? Is there some because, you know, for matrices you have even a theorem that up to an isomorphism, you have a very unique way of embedding of some matrices into another matrices.
You mean, but
Unital embedding has a unique, up to isomorphism, has a unique block structure. Okay?
Can you give me an example of a unital?
Of course. If you have a, so first of all, you know this congruence for dimensions.
Sure.
So for matrices you have this condition. But then
yes.
your counter domain becomes a tensor product of matrices.
Yes.
And up to isomorphism, this simply is an identity with respect to this decomposition to the tensor product, which means that your algebra map puts this algebra into blocks, square blocks. Okay, so you know everything about this, the shape of this map. Your formula is very concrete.
Yes.
Okay, so I'm interested what is the shape of this image inside of this matrix algebra with entries in another Kunz algebra. It must be something which could be drawn.
Well, but here you have first bummer. Notably, once you have a matrix algebra, even when you view it with some grading, okay, you still do not recover the graph. You can have very many different graphs giving you the same.
But this precisely corresponds to this property that this rigid shape of the image is up to isomorphism, of course. But once you have, if you choose a basis, for instance, okay, then you have a rigid shape of the image of one matrices sitting inside high matrices. So I'm asking about a similar phenomenon in this case.
Well, we never asked this question. I guess it's computable.
Yeah.
There are formulas, so
maybe some interesting graphics for showing this shape.
Yeah. Because the other way around, you can always go. You can play around with graphs, apply our formulas, construct some graph and path homomorphisms, combine them, and write a formula, and then you can look at the image. You can see how it looks like. Yeah. But we haven't done it, right?
It could be a nice picture to show.
But we haven't done it.
One has to experiments, like to look at some explicit matrices, maybe to guess some.
Yes, explicit matrices.
Yeah, because of course you can put it diagonally, right? Like double box and sort of this, yes. And then it's unital, of course. Yes, I agree. Okay, anybody else? You guys know. So let us thank Jan again. Thank you so much.
Thank you for the invitation.
Dimitri, I forgot. Do you have a question or not? Okay, so let me stop the recording. Stop.